Okay. Let's get started. So we're starting a new topic. And this is, I think, easier than learning chromatography and spectroscopy. It's more applicable or application-based. And there will be, from now on, a lot of calculations. So this is kind of the second half of the semester where we'll be doing more of applied analysis and a lot of calculations. So we're going to start with proximate analysis. Can someone tell me what we mean when we say proximate analysis? Without looking further into your notes. When we say proximate analysis, does anybody have a clue what we're analyzing? It's okay if you don't. Can you guess? Evita?
Calculating an approximation and not
Approximation of what? Do you have any idea? It's an approximation.
maybe nutrition labeling, like what's inside.
You're close. So, yeah?
Would it be like fats and like proteins and stuff?
Yes. So, it's proximate analysis is the analysis of the major components in your food. And it's approximation. So, it's crude analysis of the different major components. So, what are the major components in food? Without looking further. You have food chemistry, you had intro to food science, you should know the major components of food, Samantha, Tammy. Pat, Sam.
I can eat any of them. Are okay. So your macromolecules, like your lipids, your carbohydrates, your proteins.
You're missing a big one.
Uh,
Carbohydrate, proteins, lipids or fat. A big one, yes. Moisture. And what else? What else is often forgotten?
Vitamins and minerals.
Vitamins is micronutrients. Minerals are part of the ash content. Okay, so we say ash content. So everything every organic matter, vitamins are organic matter. So when you put your sample in a muffle furnace and everything burns off, vitamins burn off as well. So vitamins are not going to be in your ash sample. And this is a common mistake when we talk about ash. People think, oh, it's minerals and vitamins. No, it's just minerals and any inorganic matter that could be potentially a contamination. So proximate analysis is the analysis of protein, carbohydrate, fat, moisture, and ash. These are the main 5 components, and when we analyze them in a way that will give us a crude or approximate amount of these components. Okay, so all of these different components account for 100%. So the percent moisture in your sample plus percent ash in your sample plus protein plus carbohydrate all constitute the whole. We do not include vitamins or acids or flavor compounds because they're present in a very, very small concentration. So they really don't account to a measurable amount or an amount measurable in comparison to these major components. So that's why these represent the 100%. And I think this is an approximation. Okay. Out of these main components, what do we have on the label? What do you see on the label?
Fat, saturated fat, trans fat, and then you'll have carbs, fiber, sodium.
No, don't list them all. Out of these 5 components.
Fat, protein, carbs, and then you'll have sodium.
Don't list them. Out of these 5 components, you have carbohydrate, proteins, fat. You do not see ash or moisture. Okay? So There they are. So we have the total fat, we have total carbohydrate, we have proteins. Okay? So in your food, out of these compositional analysis or proximate analysis, we only have 3 components that show up on the label. But all analyses are required for nutritional labeling. Why? When you want to label, you have to do all of them. Can anybody think of why? I don't expect you to know. Maybe there's a miracle and somebody will know. No miracle in the air? Okay. So think of your food as a pie. Piece of pie, not this pie. This pie. Okay. So think of your food as a pie, and you have moisture, you have fat, you have ash, you have protein. What's left? Carbohydrates. Okay. So we use analytical tools to analyze protein. We analyze ash. So we do protein, you'll learn about that, Keldal or Dumas. We do ash by dry ashing. We do fat, although success and vagina are official methods of analysis, but to report fat, we use the method that you've done in the lab, the GC analysis, but instead of just doing a qualitative, they do a quantitative of all fatty acids, and then they add them up and account for glycerol and water and calculate the amount of fat. This is how they do it in official method. So we have the fat determined by GC, we have the ash determined by dry ashing, we have the moisture determined often by oven methods. We'll talk about that today. And then we have all of these 4 components. What's remaining is total carbohydrate. There is a chapter on total carbohydrate characterization, and we're going to learn that total carbohydrates are very complex. So there is not one method that will measure all carbohydrate in a complex system. So total carbohydrate composed of sugars, starches, fiber, small saccharides. So there's so many different components of total carbohydrate, and there's not one method. Even if you want to calculate or determine amount of sugar alone, amount of dietary fiber alone, amount of starch alone, amount of triglycerides and smaller saccharides, and then add them up, you might get a value that is greater or smaller than this, what's left in the pie. So you might get this much, or you might get this much. We don't want that. We want to add up to 100. We don't want to individually measure all the components and approximate it to get to over 100. We don't want that. So we measure moisture, ash, fat, protein, and by subtraction, we get total carbohydrate. And that is what it is used for your nutrition label. This is how they determine total carbohydrate. And then they do a separate assay for dietary fiber, a separate assay for total sugars. So, but for determining total carbohydrate that goes on the label, it is by calculation, subtraction from 100. So you measure all of these individually and then subtract from 100. So now you see, now to answer this question, now you know this, all of this. So why do we analyze everything for nutrition label? It's right there in front of you guys. I know you know. Come on. It's a Friday. Who wants a +2? You just answered. Amanda. What? No. What know you know. I'm gonna call out names or walk out. Yeah? What? What did you say? No, I'm not yelling at you. I couldn't hear you. What did you say? I mean, why would you want ash or moisture for health concerns?
To get the exact 100%.
Yeah. To get what? Say it.
To get the exact 100%.
To measure the amount of total carbohydrate. To get the amount of total carbohydrate.
To make it 100%.
To make it 100% and to put it on the label. Okay, I'm walking out. Keep on going. I didn't know that you didn't like me that much. Okay. So we measure fat, protein, ash, moisture, so we get the total carbohydrate. If we don't measure ash and moisture, we cannot get the total carbohydrate to report on the label. Simple. Okay. Now that you're geared with this knowledge, let's move on to different components. So you will have, we'll talk about moisture, then next week ash and protein, and then later on we'll talk about total carbohydrates. So we will have these designated sections for the proximate analysis. So today we'll start with moisture analysis. Okay. The following is true. Oh, Paul is ready. Go ahead. All of them are true. Okay, what else? Who else had their hands up? Anne?
I'm going to say all of them.
All of the above. What else? April?
It's just B and C.
B and C.
I think it's just B.
Just B.
Just B.
Just B. Michelle. What? No, say it. Say it.
No, I was.
What did you say?
I was thinking. I said none of the above. Just
None of the above.
Let's just kind of.
Hated. None of the above. Thank you. You wouldn't want to say it, but it's correct. Okay, be confident. The weirdest answers could be the right one. So yes, none of the above. Moisture content and water activity are two different things. We're going to learn about that today. So water content and moisture content are used interchangeably. So you can say the water content and the moisture content. But water activity is completely different. So two products can have the same moisture content but different water activity. Why is that? Food chemistry students, why is that? All of you either in food chemistry or taken it last year. So you should know this. Food science majors. Okay, I'm going to truly walk out. Will. What's that? Okay, if Ted hears you say that, he won't like it, but that is kind of correct. So, free water, what do we mean by free water? Free water is kind of not a really correct term, but the water that is not interacting with other constituents and is available for reactions, whether available for microbial growth or available for chemical reactions. Okay, so they cannot be used interchangeably. All right, all methods for determining moisture content are based on evaporating moisture and measuring dry matter. No, there are so many different ways of measuring moisture. Next week, you're going to be learning about oven methods and measuring difference in weight, but also you're going to be learning about a chemical assay, the Carl-Fisher, which is not based on measuring the change in water upon heating or change in weight due to loss of moisture. It's a different reaction. And there are so many different methods. There are physical methods, there are oven methods, and there are IR methods, for example. measuring the bending and stretching of the water molecule bonds. Okay, moisture content is an accurate indicator of perishability. No, it's not. It's the relationship between moisture content and water activity. So it's not moisture content alone. Okay. All right, isotherm, your favorite subject in food chemistry. A relationship between moisture content and water activity. Used to provide information about the moisture content, water activity where you have the most stable condition. A tool that can be used to predict shelf life. B. Any other takers? I'm waiting. Hayden? Give us your wisest answer. So I'm gonna go next to Alex. B. Okay. Maddie? Just say a letter. Huh? C. Any other takers? Okay. Who has taken food chemistry? Or who is in food chemistry right now? Hannah. Did you talk about isotope? No. You didn't talk about isotope? No.
I think
What?
I don't know. It was on a graph this morning, but I don't think we talked about it.
Oh, is he still lecturing?
He just for this week, he took a look at oxidation this week.
Oh, so he didn't talk about moisture, water yet?
That's the first thing he talked about.
What?
That's the first thing.
Yeah, so he must have mentioned isotherm. Okay, all of the above. What did he say? Oh yeah, good. Yeah, all of the above. We'll see the plot. The isotherm is a plot between moisture content and water activity, and it gives you an indication of the most stable condition. We'll talk about monolayer later on and what that means and how we actually determine that in food analysis. And it is used as a tool to predict shelf life, and we'll talk about that later. Okay. Yes?
So on the previous slide, it says that it's a tool that can be used to predict shelf life. So is that isotherm on its own?
Isotherm and all the information that the isotherm gives you, like the monolayer and the multilayer and the moisture content and the water activity of the different food products. So the whole picture. Yeah, we'll discuss that later. Okay, so next, define moisture analysis. When I say moisture analysis, what do I mean by that? What am I analyzing? What am I analyzing? Moisture content is half the story. So when I say moisture analysis, I'm looking at both. I'm looking at moisture content and water activity so that I can get the entire picture. So each one of them tells me something different, and the interaction of them gives me an idea of the perishability of the food, the structure of the food, the breaking point of that food. So it's really the entire thing. So moisture analysis doesn't mean only determining moisture content. It's both. Okay. I think we touched on that a little bit. What's the difference between water content and water activity? Okay, so we did touch on it, so let me just show you. Water content or moisture content means the same thing. Is the total quantity of water. When I say not chemically bound, because most of the compounds in food, they're formed upon condensation. So that means, okay, when amino acids form, they form a peptide bond, it's a condensation reaction. Maillard reaction is a condensation reaction. Formation of triglycerides is a condensation reaction. Formation of disaccharides is a condensation reaction. So there is a loss of water, okay? Or water is bound in the chemical form. So when I hydrolyze sucrose, I'm releasing water molecule and also releasing the two separate saccharides. So water is actually in the form of the triglycerides, in the form of the protein, it's in the form of sugar. So when I say water content, I only mean the water that is not chemically bonded. You might have water interacting with different constituents, interacting via hydrogen bonding, dipole moment, but it's not chemically bound. Okay. So something you need to know that the dry matter that remains after water removal is referred to as total solids, which is a very important parameter for food quality in general, or quality of the food product. So you can, sometimes people ask you, okay, so what's the total solids versus what's the total moisture content? So the total solids plus moisture content is the entire food, right? Water activity, in literal term, what it is, it's basically the relationship between the partial pressure of water in the atmosphere above the sample relative to the pressure of water itself. So the vapor pressure of pure water. So it's a relativity. That's why we call relative humidity. It's a relativity. So water activity is the equilibrium relative humidity by 100, which is the vapor pressure of water. Okay, so you have your sample, and then when the sample sits and reaches equilibrium, the pressure of the vapor in the atmosphere relative to the pressure of the vapor of water gives you the water activity. So the higher the water content in the sample, there is a relationship. It's not always linear. But the higher the water content, you will potentially have higher pressure of water in the atmosphere above the sample. Okay? But even if you have two samples with 50% moisture content, but one has more total solids, like sugars or salt, than the other, the vapor pressure of the one that has less salt and less sugar will be more than the vapor pressure in the atmosphere for the one that has more salt or more sugar. So then you will have less water activity in the sample that has more salt, more sugar, than a sample of the same moisture content that has less water, less salt, less sugar. Okay? So, what type of product will have a water activity of 0?
Like salt.
Salt that does not have any moisture in it.
Oh, so that like.
So salt could be salt, but it's completely dry salt.
Okay.
Yes, it could be anything that is completely dry, no moisture whatsoever in that sample. Then definitely you don't have any water activity. Okay. What's water activity of 1? What kind of product or sample will have water activity of 1? Huh? Soup? So when you drink soup, does not have anything in it? It's just water? Just water. Okay. Importance of moisture analysis. Moisture analysis, that means moisture content and water activity. Huh?
Packaging and shelf life.
Packaging
Shelf life.
and shelf life. So okay, there are two different things. I'm going to say packaging and shipping. Why it's important? Because sometimes you reduce the moisture content to extend the shelf life, right? And to package to have better, more convenient, more efficient packaging. So like concentrated orange juice or concentrated milk. So you would have less container, smaller container, and lower moisture content, extend the shelf life. Okay, what else? Sammy? Microbial growth. So it's important. So high water activity, 0.8 or higher, is correlated with microbial growth. What else? Yeah. Texture of food, yes. So if a sample of a food picks up moisture, it can potentially become soft, soggy. We don't want that. Okay, quality. So we're talking quality of food. Good, good. There's one important one. We started with it at the beginning of the lecture. So nutrition label, yes, carb determination. So we talked about all this, preservation, stability, so lower water activity, higher stability, quality factor, we talked about that, convenience of packaging or shipping. Oh, this one we didn't talk about, meeting compositional standards and standard of identity. For example, milk, 87% water. If it's above 87% water, it could be adulterated. Okay, so also for different cheeses, you have a certain amount of moisture that is allowed. So this is standard of identity. So every product that has standard of identity will potentially have a required moisture content. You'll see that we will calculate content on wet bases and dry bases. This is a very common thing in analysis or reporting of data because you want to eliminate the impact of moisture. Because different foods pick up moisture. So when you analyze food can be different moisture content. But if you want to compare them in their protein level or compare them in their fat level, you want to eliminate the fact that they're different in moisture. So often you report your values on dry bases. So even water is reported on dry basis too. So when you plot the isotherm, the water is as a ratio to dry matter. So it is on dry basis. So the amount of water with respect to the amount of solids. So when we say water on dry basis, to you this doesn't make sense. Water on dry basis, how can that be? Water is water. It cannot be dry. But no, it is actually a ratio of the water amount to the dry solids amount. That is what it is, water on dry basis. So it's just a ratio of water to dry solids. Okay. We have challenges in moisture analysis like anything else in life. We have challenges. But let's look at the water molecule and its structure. So the water has the oxygen and two hydrogen, and then the oxygen has two free pairs that can be proton acceptors, and these two hydrogens are proton donors. So that is the principle of hydrogen bonding. So the hydrogen bonding is the bonding between an oxygen or an electronegative atom and hydrogen. So the two pairs can potentially bond with this hydrogen here and form the hydrogen bonding. So when you have water, so these molecules are in constant movement and interaction with each other. And with more heat, you have more movement of these molecules. So, but this bond is weak. It's not a strong bond. So the relative humidity in the air versus the temperature can cause a different movement of this water. So what does that mean? What am I talking about? I'm talking about if you put your sample out here, no matter what the temperature of the room is, there is humidity, and there is humidity difference between the atmosphere and your sample. So water is going to move in and out because the hydrogen bonding is weak, and the more water is just going to move. Constantly, water molecule is going to move. So then even though you're not heating, if you put your sample out for a little bit in the open, if it's dry sample, it's going to pick up moisture. If it is a wet sample, it's going to lose moisture. So this is very important in moisture content analysis, because you have to take into consideration the fact that when you process and handle your sample, you do not want to have any loss or gain in moisture, because that causes error in your analysis. So basically, you need to minimize losses and gains during sample collection, sampling, and sample preparation prior to moisture analysis. This is very important. You'll see in the lab that you will be weighing your sample and directly putting it in a desiccator. In the desiccator, there will be a desiccant in it. So it's going to, the environment in the desiccator doesn't have moisture floating around. Okay, so your sample will not absorb moisture from the environment. So then you put it in the desiccator, and then you put it in the oven, and when you take it out of the oven, you put it in the desiccator again. So you always have to watch out for that. And during sample prep, you want to make sure that you don't leave your sample out for a long time. Even in cheeses, for example, moisture loss can happen very, very quickly. So we have to be careful with that. Also, in moisture analysis, moisture content analysis, we have to measure the amount of water no matter what state it is in, solid, liquid, or vapor state. So that could potentially be another challenge, to be able to accurately determine the amount of water in all of the different states that it could be present in. Water interaction with food ingredients. So water is also forming hydrogen bonds with different components, and dipole-dipole interactions, and van der Waals interaction with sugars, with salts, with proteins. It's interacting. So the more complex your food sample is, the more the water is going to be interacting with these different components, the harder it is to accurately measure all of the water content in your sample. And that's why we say approximation, crude, because it's almost impossible to be able to measure every molecule of water in your sample, especially if your sample is of complex nature. Whew, moisture analysis. We have like 20 different methods, maybe 25 different methods. There's so many different methods for measuring moisture content. So we have the oven-based methods, and you will be doing those in the lab. We have the forced draft oven method. We'll talk about it. Vacuum oven, microwave. So we'll be doing that. We won't be necessarily doing the rapid moisture analyzer, but we do have one in our department. I'll talk about it quickly. Thermographic gravimetric analyzer. So basically, this is a block you put your sample in. You heat, and it's constantly taking the measurement of the weight. Lyophilization. This is another method. Lyophilization, who knows what it is? Have you heard this term before? Have you heard freeze drying before? Yeah, it's freeze drying. So basically, sublimation of the water. So the water goes from a solid state in the ice form to a gaseous state. So you can measure moisture content that way, but it's a very expensive way of measuring moisture content. You don't do that unless it's research-based. Chemical desiccation, talk about that. Carl-Fisher titrations, chemical-based analyses. So different, and they're all direct methods. They all measure directly the water content, one way or the other. Indirect methods, measuring a different property of food related to the presence of water. Graphic, for example, gravity or density, specific gravity or density, like the hydrometer and pyranometer. Refractometer, we'll talk about all of these dielectric capacitance. Freezing point, microwave absorption. We talked about NIR last time, so it's measuring water with NIR absorption, but requires calibration. Conductivity. So there's so many different ways to measure moisture, and we'll talk about most of them. Not all of them, but most of them. So oven drying method. These are the simplest, easiest methods that you can encounter, but they take time. So you have to put them for a certain amount of time, measure your sample weight before, measure it after, and then determine the loss in weight. The loss in weight would be the water that got evaporated. That would be the weight of the water. So usually the way you standardize these methods, if you're working with a non-AOAC method or a product that doesn't have an AOAC method, usually methods are either approved by AOAC or by AACCI. So for every food product, they give you the time and temperature combination in different ovens to use in order to get to as accurate as possible of a moisture content. But let's say you don't know that. So the way to determine the best time and temperature combination, or you select the temperature, and then you monitor the weight of the sample over time. When the sample reaches a constant weight, you know that this is done. You're done. All of the moisture that is possible to evaporate is evaporated, and then you get your final moisture content. So the way to calculate percent moisture is simple. So you get the weight before and then the weight after drying, and that would be the amount of water by the amount of the sample that you started with, the wet weight. So let's say you weigh 2 grams, and then after drying the sample is 1 gram, so you lost 1 gram, that's 50% water. You have 50% in the sample. So now determining dry bases, you're going to be doing that in the lab. So you will be looking at the same thing, the difference from wet to dry, so you get the moisture content, and then you divide it actually by the dry weight. Okay, so dividing it by the dry weight, you're actually getting a proportion of moisture to dry matter, and then you multiply by the 100. Can this value be over 100? Can the dry bases be over 100%? Thea, what did you say? Did you say yes? Yes. That is correct. Yes, it can. Take processed cheese. So whoever is going to be the group of processed cheese is potentially greater than 50% moisture. So that means you have, if you say 52, if you have 52% moisture, so 52 grams in 100 grams, that means you have 52 over 48 grams of dry matter. So that's going to be over 100%. Okay? So yes, if you see dry base is over 100%, don't freak out. It depends on the moisture content of the sample. But percentage on wet basis can never be 100%. You cannot have a part bigger than the whole. So if you make a calculation and percent on wet basis is over 100%, go back. Something is terribly wrong. Okay? You cannot have a part bigger than the whole, and the whole is always your wet basis. Okay. So consideration. Some sample requires pre-drying. If you're using a vacuum oven or if you're using a forced draft oven and you have milk, milk is mostly liquid. If you put it there, it might boil, splatter, get errors. So the common method of doing the moisture content of milk is you actually pre-dry it in a bath, a water bath, at low temperature, so it gets a little bit concentrated. Definitely you have to take the weight before you do that, and then you transfer it from the water bath into your oven, whether it's a vacuum oven or forced air draft oven. So sometimes you need to do that. So when I say steam bath, meaning you put your water in a bath and then it's like boiling, and then there will be steam, and then you put your sample over that on something that has pores, and then the steam will heat up your sample and cause it to dry out a little. Not the direct contact, so that you don't have splattering. Okay. Another consideration is that you might get decomposition of food constituents. So the decomposition or the chemical reactions that can happen might cause either overestimation or underestimation. I'll give you an example of overestimation and give you an example of underestimation. So overestimation, if you have high heat, or let's say 100 degrees Celsius, and you kept it for a long period of time, what could happen after removal of water, you might get Maillard reaction if you have protein and reducing sugar, and Maillard reaction is a condensation reaction. Okay, so with that, the condensation reaction, you lose water. Okay, so you lose water, water evaporates. When water evaporates, then you're adding the amount of water that was lost, so you get an overestimation. You get less dry matter. Okay, so it's an overestimation. Burning of sugars and burning of carbohydrates, you also lose water that way, and water evaporates. So now you're losing the chemically bound water. When you do that, you get overestimation. However, take lipid oxidation. Lipid oxidation is interaction of lipid with oxygen. So the dry matter weight actually increases. So you actually get underestimation of water. Okay. Loss of volatiles. Loss of volatiles is basically when you have volatiles in your sample that will evaporate with the water. So that causes overestimation. Example of volatiles. What could evaporate from your sample? Other than water. If you have alcohol, yeah. If you have acids that are volatile, acetic acid is volatile. What else could be volatile? Flavor compound. Okay, so you can actually cause an overestimation if you have some losses in volatiles. Temperature control. This is very important in the different ovens. So sometimes you don't have good distribution of temperature within an oven unless you have a forced air draft oven, which you have in the lab. So there is air circulating, hot air is circulating with a fan, so that wherever you put your sample, you have the same distribution or the same heat. However, if you use convection oven, so you put your sample and the surfaces are heated rather than air circulating, you have different distribution of heat. If you use vacuum oven, the one that we have too in the lab, there's also no air circulating. Again, there is differences in the location for the distribution of heat. So this can impact your precision. You might have poorer precision in ovens that don't have circulation of heat. Pans and covers. So what you will be using in the lab is disposable types of pans made of, what is it, aluminum pans? But there's also metal. You can use metal type. I don't know, what kind do we have? What is it? The metal? No, the disposable are aluminum, but the metal containers they're not stainless steel. Tin. Yeah, cheap. Tin. Sometimes they come with a cover. So obviously you want the moisture to evaporate, right? So when you weigh your sample and put your sample in, you don't want to put the cover on it. So you can put the cover next to it, especially if it's labeled. So you would put the cover next to it, and then before you take it out, you cover it so that nothing spills over or nothing gets blown away. So you can do that. Sometimes this is fancy. You'll have a cover that is kind of a mesh cover, so it has pores. So you put it on there so that you protect the sample from blowing off if there is air circulating, and then the moisture can evaporate through the pores. That's pretty fancy, could be expensive, but the cheap way that we're going to do it in the lab is you have those aluminum disposable ones, and then we have glass wool. So to protect your sample from blowing up, especially like baby cereal, any powdered sample might blow up from the air circulating, you take a little piece of glass wool and you put that on top to prevent blowing off of your sample. Surface crust formation. So preventing surface crust formation. First of all, your sample needs to be in a small particle size, as small as it can get for moisture analysis. I think 20 to 40 mesh is where that lies. So it needs to be homogeneous. It needs to be in a part. The smaller the particle size, the better. But of course, if you have cheese, you're not gonna be able to have, like in this particle size, it would be shredded. So don't pile your shreds on top of each other. Spread them out in the pan as thin as you can. Because what happens if they are piled up and there is a certain height, a thick height, you can form a crust by burning the surface, and then the moisture inside is trapped and it won't evaporate. So you really have to have a thin layer, very well distributed. Sometimes some type of samples are sticky type of samples. They might stick together when you are evaporating the moisture. They might stick together and they form a crust. So in these type of samples, they put sand. So they put clean sand in there. One last slide before I let you go. Well, I thought not even halfway. What happened? Okay, so there are lots of errors. Particle size, we just talked about it. We need to have a small particle size as possible. We can lose volatiles that cause overestimation. High temperature can lead to chemical reactions and loss of chemically bound water. And the chemically bound water can lead to overestimation when it's lost. Lipid oxidation leads to underestimation because the dry matter will be higher due to picking up of oxygen and reaction. Sample could be hygroscopic, taking up moisture from the atmosphere, leading to erroneous results. Changes in carbohydrates by burning or reaction through Maillard reaction. Surface crust, we talked about that. Splattering, we talked about that. Improper storage in desiccator. So if you have a saturated desiccant, so it's no longer absorbing moisture from the environment. So you want to make sure that your desiccator is dry, has the right desiccant in there, and have your sample in the desiccator at all times. Okay, do you have half an hour? No. Okay. You can leave. Have a great weekend. We'll continue on Monday.
It's like a story.